Good morning. My name is Trang Thai, and I'm presenting on behalf of James Cooper. Unfortunately, he couldn't make it here, and we are PhD students in Athena group, led by Professor Manos, Tentzeris at Georgia Tech. And so the talk today is about isotropically radiating cube topology with isolated core for wireless applications. I will try my best to answer the questions on behalf of James. So the goal of the design, starting with isotropic radiator. So the thing is, in RFID sensing, we want the sensor itself to be isotropically radiating, so that we would have orientation independent. But the problem with this is that usually if we have some processor or any circuitry that would like to embed it with this antenna, we would have some detuning for both the antenna and the circuitry. We want some isolation, and we want some surface dependent as well, so you can just put the sensor anywhere. So the isolated core is desirable for embedding problem. Now the next thing is we want to be able to match this design to any standard RFID chips. As I say, RFID is very attractive technology for long distance sensing. But if we can match it to any standard RFID, it means we can match it to any load with any significant real part. Having that design goals in mind, we start with the cube construction. So here we have this cube that start with metal layers here. All faces, 6 faces, covered with metal. Now on top of the face will be an FSS EBG, what stands for frequency selective surface and electromagnetic band gap. I will explain the working operation principle of this one shortly. Now on top of that, so notice we have a gap here, and then we have a gap between the FSS with the dipole. So this is just a regular conventional dipole that wraps around this cube. So what are the function of each? So this box right here covered by metal will acting as a core. What it means that inside this you can put anything, circuitry, processor, and will be isolated from the environment outside of it. Of course, you can also have hole in there, so it's supposedly if you want to do gas sensing, the environment can access through the circuitry too. Now, this one will acting as a reflector that be able to have constructive interference. At the same time, will retain the isotropic radiation of this dipole antenna. So, just a quick review on material. I would like to show you why we use this EBG structure. So first, we know that for omnidirectional structure, the best is like dipole and antenna. It's small size and also easy to fabricate. But the problem is, if you put the dipole antenna on any metallic surface, you will have a mirror current and you have a destructive interference. So you detune your radiation of the antenna. But we do want to have the surface. Why? Because we want isolation. So the solution is to use the FSS. What it means is that it's the construction of 2D periodic structure, and each of these unit cells is a resonance structure. Basically, think about this. If you have an incoming plane wave, TEM waves, then it will be able to excite the resonant behavior of each of these unit cells. And then these cells together will act collectively as band stop filters. So in the pass band, you kind of have transparent ideally, and in the stop band, this structure here on a planar surface will appear like a PEC, which is a perfect electric conductor. Now, if we just put so if we have a dipole sitting on top of a ground plane, we definitely have a detune. We have a destructive interference. But by adding this structure on top of the ground plane, what happens is that this ground plane now acting like a mirror. So think about this one as an equivalent with having this one a copy of this FSS structure on the other side of the ground plane. Take the ground plane away. What you have here now is that, of course, when this incoming wave hitting this FSS, it will also have a reflected of 180-degree phase shift as it appears as a PEC. However, you have another copy structure at the back, which is in mirror as a mirror structure of this one. Now together, these two planes will give you a constructive interference, and that means in this case you have an artificial magnetic conductor. This is what we want, because when whatever the reflected back, we will have a constructive interference. So this is basically how it works. Some interesting animation here that James made. So the design is started with tuning of the unit cell. So we make some huge assumption to start with, and the rest was mostly optimization through simulation package like CSD. That's what we used. And we have, the way we set up is we have an infinite array with master-slave boundary conditions and a broken port. This one sitting on top of the ground plane, also infinitely. And we start with the tuning for this for the frequency range that we're interested in. So we take that and then we further wrap it into a cube, also in simulation first, and then we have to apply further optimization. And the next thing was to fabricate, do the fabrication of this structure. We chose the inkjet printing approach because with this approach we can fabricate with paper, and silver nanoparticle tip will give us low cost, low impact, and rapid prototype. Of course, the core in here you see made from copper tape, homemade device. Simulation result and measurement. Now this red line right here, solid line, is the E-plane simulation result. This is a radiation pattern, and the dashed line of some of the red is the S-plane. The green curves are the measure result. Notice that in this fabrication process there are a lot of variations because the manual process, the gap between the dipole is hard to the dipole and the FSS surface, and also the gap between the FSS surface and the cube face also hard to control. We cannot have precise distance that we want in the simulation. So, however, well, as in any variation, you will have sometimes, most of the time, you have negative effect. In this case, we have a positive effect. So our measure result is better in the sense that it meet our design goal better. We have a better isotropic radiation pattern. As in matching, it turns out we also have a really good matching without any further matching circuitry, and we don't want that. So if you look here, this is the real part, and this is the imaginary. This is the absolute value of the imaginary. We want conjugate matching, and we are looking at the absolute value of these two, the chip and the cube. And we see that they have in this range from in the 900 megahertz range, we have a very close, a very good match. And looking at the reflection coefficient around this range, we have, like, you see negative 15 dB at least from here and to the rest. What it means is that we achieve at least 90% efficiency of power transfer. So what it shows here is that, in conclusion, what it shows is that we can achieve matching, we can achieve omnidirectional radiations, and we show that with this approach, you can, by the cube itself, you can have application like using it for a tornado study because the cube's mechanical topology is stable. But further, we can also have this approach to any structure, any conformal surface that you would like to implement sensing. So that's why we call it smart skin, because this approach allows you to implement sensor circuitry and sensor nodes into any sort of surface and have good have good power transfer without much of the interference, and you have orientation independent as well. So thank you very much, and I will try to answer the question for James.